Hi everyone, my name is Sai Manikandan and my teammates are Neha, Uday and Upasna. The title of our project is Motion Planning of Mobile Robot in Dynamic Obstacle Environment. Motion planning for robots is like creating a map or a set of instructions for the robot to follow to move from one place to another. It's like telling the robot where to go and how to go. In a static environment, the surroundings of the robots doesn't change, so it's easier for the robot to navigate. However, in a dynamic environments, things around the robots are constantly moving, like people, objects moving around, making it difficult for the robot to plan its motion. This is an active area of research, and many scientists and engineers are working on developing ways for the robot to navigate and plan their motion in dynamic environments. Delivery drones are a prime example for this, given the increasing number of deliveries that are being carried out by drones, and companies, irrespective of being small or big, are investing heavily into this domain, with companies like Amazon, Walmart, UPS leading the way. Also, given the restrictions that drone have with respect to the flying zone limit, and also with increase in indoor deliveries like in warehouses, we plan to carry out motion planning for a drone in a dynamic obstacle environment. For our literature review, we found out that non-linear model predictive control (NMPC) and velocity obstacle algorithm are better algorithms for dynamic obstacle environments compared to traditional algorithms. And we found few researchers who have worked with these algorithms in multi-agent environments. However, as our use case focuses on delivery drones, we went forward to implement this with single agent robot. So the objective of our project is to implement velocity obstacles approach and non-linear model predictive control for a single agent robot in a dynamic environment like a delivery drone. The environment we consider is a 2D space environment, and we will be quickly working implementing the algorithm in gazebo environment as well. So let's take a look at the non-linear model predictive control. Initially, we will establish the environment which consists of dynamic obstacles. Then the start and end goals are defined for the robot. Once these initial parameters are set up, the path planning loop is initiated. This loop runs for a particular amount of simulation time that is predefined. So inside the loop, the robot first predicts the future positions of the surrounding obstacles based on the velocity and direction of motion of the obstacles, based on the current state and the end goal of the robot. A reference trajectory is computed for the robot to follow. In order to get the robot to its end goal, the control algorithm computes an optimal velocity that will enable the robot to avoid all the obstacles and yet reach the end goal. The control algorithm that is working in behind the scenes is basically an optimization problem. But the goal here is to minimize two kinds of costs: the tracking cost and collision cost. The tracking cost is the difference between the goal position and the current position of the robot, while collision cost is a measure of risk of collision between the robot and the surrounding obstacles. Once these costs are found, the sum of these costs are taken, and the cost function thus obtained is minimized using sequential least squares programming optimizer, or the SLSTP algorithm. This particular algorithm is chosen specifically because it is capable of minimizing functions of several variables with any bounds, equality, and inequality constraints. Now, coming on over to velocity obstacles path planning, the environment setup is basically similar to the NMPC algorithm that we saw in the previous slide. Uh, the environment is set up with the dynamic obstacles, and their motions will be predetermined. The robot is spawned in its start location, and its end goal is also specified. A loop is started, which runs for the amount of specified simulation time, and inside this loop, based on the constraints produced by the surrounding obstacles of the robot, an optimal velocity is to be computed. The computed velocity is updated for the robot and it may also be stored. It can also be stored in order to have a better visualization. So, in contrast to the NMPC algorithm that we explored in the previous slide, the robot here is in real time, tracking the motion of its surrounding obstacles and then adjusting its own velocity so as to ensure collision avoidance. Whereas in the NMPC algorithm, the robot is actively predicting the future positions of the obstacles surrounding the robot in order to have a better chance at creating a proper path for the robot.
Coming to the challenges that we faced, during our simulation, there were certain test cases for which we could observe that the robot is not moving from the initial position to the goal position. At these times, the robot would stop navigating even before it reaches the goal position. Currently, we are in the process of debugging. Coming to the model predictive control, it is based on the vehicle dynamics of the system. So a slight change in temperature or moisture in air can give erroneous results. Thus, a strong vehicle dynamics model that considers such conditions needs to be included. Coming to the results, we have here implemented the velocity obstacle algorithm. In the sample 1, you can see that the robot is avoiding dynamic obstacles and moving from the bottom left corner to the top right corner from 0, 0 to end goal position of 10, 10. In the sample 2, the robot tries to stay at 5, 5 while avoiding collisions with the dynamic obstacles. Next, we come to our non-linear model predictive control. In this, we have used the similar sample cases as the previous algorithm. Here, in sample 1, you can see that the robot is moving while predicting the movement of the dynamic obstacles and when it is further deciding the optimal path. In sample 2, the robot again tries to stay at the center. In these sample cases, you must have observed that the dynamic obstacles are colliding with each other. That is because our project mainly focuses on a single agent decentralized robot, which avoids any kind of dynamic obstacles on its own. This is optimal for real world applications such as delivery drones.
Looking at the task list, we have completed the phase 1, phase 2, phase 3, and phase 4 of the anticipated schedule. Me and my team have made significant progress and will continue to do so. In the foreseeable future, we plan on implementing the algorithms in Gazebo or any other 3D environment by March 20th. Further, we plan on completing the documentation work in the next week, that is March 28th. Looking at the schedule, we will have enough time to modify the algorithm and make it more robust. Coming to conclusion in future work, after conducting rigorous literature survey, we have deduced that model predictive control and velocity obstacle algorithm performs better than the traditional algorithms. We implemented these algorithms in a 2D space environment with dynamic obstacles. We are also aiming to implement the same in a real world environment like Gazebo. Thank you.